Today we're going to be looking at the limit definition of a derivative. So yesterday we talked about secant lines. Today we're going to be talking about tangent lines. So in just a moment I'll give you an illustration of what we're talking about. But basically we're switching from talking about the average rate of change to talking about the instantaneous rate of change. So what's the slope at a specific point versus what's the slope on an interval. So for that, we've got this definition. We're looking at the slope as we get really, really close to that point. We're going to have an animation that we look at in class that and in this video that kind of illustrates what we're talking about. So we've got the two different ways or notations for talking about the derivative. One's if we write our function in function notation, f of x, and the other is if we write it as y equals some expression. So for the function f of x, we write our derivative as our first derivative of x as f with that little apostrophe in the air of x. The way we read that is f prime of x. On the other side, where we write it in terms of y, we've got our derivative as dy over dx. And that dy over dx just means the derivative of y with respect to x. And think of those d's as deltas. It's telling us the instantaneous change in y over the change in x. Let's look at graphically what we're talking about now. So yesterday we talked about the slope of a secant line. So on an interval, what's the average rate of change, the slope on that interval? Now today, our derivative at a point is talking about at a tangent. So at a specific point, C on our curve, what's the rate of change? So it's instantaneous. It's no longer on an interval, it's just at that specific point. So what we're going to be doing is finding equations for the derivative at any point on the curve, and then we can plug in any value of C to figure out what our slope is at that point. Today we'll be doing that with our limit derivative. We'll also be finding the tangent line equations once we have found those derivative expressions. So we've got two examples we're going to look at. All right. Today you're just going to be taking notes. Tomorrow you'll be doing some practice. So we're given the function f of x equals 2x squared minus 7x plus 1. And we're going to use our limit definition that we just wrote down. Oopsie. So the limit as h goes to 0, f of x plus h minus f of x divided by h. So now we substitute in that x plus h, and this is going to get messy, guys. So it's going to get a little messy before it gets better. So I've got 2 times x plus h squared minus 7x plus h plus 1. And then that whole thing is going to be minus this expression, so minus 2x squared. Distribute the negative, plus 7x minus 1 divided by h. We have to expand the x plus h squared and distribute the negative 7. So when you do that, you're going to get 2 times x squared plus 2xh plus h squared minus 7x minus 7h plus 1 minus 2x squared plus 7x minus 1 divided by h. Remember, this is still the limit as h goes to 0. Getting sloppy here, I should have written that. All right, so we still have to distribute that too, but if we're just looking at this real quick, we do have some stuff we can get rid of. So the 1's cancel, the 7x's cancel. All right, so let's keep going. If we distribute that 2, we're going to have 2x squared plus 4xh plus h squared minus 7h minus 2x squared divided by h. So now we've got the 2x squareds cancel. And we've got this expression here. Now we are going to think about, do we have any common factors? So we've got 4xh plus h squared minus 7h divided by h. Our greatest common factor here being h in the numerator. So I've got h times 4x plus h minus 7 divided by h. H is get out of town. Then we're looking at the limit as h goes to 0 of 4x plus h minus 7. Substitute in 0 for h. You've got 4x plus 0 minus 7, or 4x minus 7. Well, what is this? We're using function notation, so this is our derivative. At any point on that curve is 4x minus 7. I probably should have written that up here too, f prime of x. Moving on to our second example, this one's going to be a rational, so it's got a fraction. So we're going to end up multiplying by LCD in our numerator. So once again, I've got my other notation now with y, so I've got dy dx equals my limit definition of a derivative, which goes to 0. So I'm going to use some algebra tricks here. This is like dividing by h, right? That h on the denominator. So I'm just going to pull that out front, just so our fraction's a little prettier to look at. Now I'm going to do my least common denominator for this part here. I'm going to multiply through by it. So my LCD, remember we just collect them all. It's like Pokemon. We've got x and x plus h. So I'm going to multiply each of these by x and x plus h. And see what happens. Try and get rid of that highlighting. All aboard the struggle bus. There we go. All right, so x plus h and x plus h cancel for this first one. X and x cancel. So I've got, switch back to black. Limit h goes to 0. 1 over h. And then I've got x minus h over x and x plus h. I'm sorry. Yeah. All right. So the x's cancel. And then we've got this h and h cancel. So we've got -1 and a placeholder 1 here. So now I've got the limit as h goes to 0 of -1 over x times x plus h. I substitute in 0. I've got -1 over x times x plus 0 or negative 1 over x squared. Suppose I could write that bigger. And that's equal to our derivative. Since it was written in terms of x, we're going to use dy dx as our notation. All right, so that was the derivative in general. So that means for any x. Now we're going to define the derivative at a point. So now we're saying, well, at some specific point, what is my derivative? So basically the process is going to be the same, except we're going to be looking at a specific value. So there's two ways we can write this. One is the same as what we were writing before. Just instead of having x, we're going to have c, our specific point. And then one is going to be instead with an x. So this one, we can more readily see what we're talking about. So this is like a change in y's on the numerator, right? And this is like a change in x on the denominator, those differences. So this is like saying the average rate of change as we get really, really close to that point. Like I said, we're going to look at an animation for this in just a minute. So we're interested in finding the derivative at -2 of this function 2x squared plus 1. So derivative at -2. We can use either of our notations. I'm going to use the first one. And we've got c plus h. Oh, I guess I'll write it out. I won't be lazy. So substituting in, I'm going to have 2 times c plus h. So let's figure out, so I've got -2 plus h squared plus 1. So that's my first f of c plus h minus f of c, which is 2 times -2 squared plus 1 divided by h. That's my limit as h goes to 0. So for this first part, 2 times FOIL, so 4 minus 4h plus h squared plus 1 minus, and this is going to be 9, oopsie, over h, and I need that limit as h approaches 0. So then I've got 8 minus 4h plus, I feel like I distributed something wrong. Hold on a second. Because I did distribute something wrong. This should be 8h plus h squared plus 1 minus 9 divided by h, limit as h approaches 0. Okay, so we've got 8 plus 1 is 9, minus 9, those cancel. And then we've got our greatest common factor here, and the numerator is h. H's cancel. Substitute in our value. We get -8. So our derivative at -2 is equal to -8. All right, the next one, we're given our equation for the function and our equation for the derivative f prime of x, and we're looking for the tangent line at 2. So we're going to use point slope here. which we did in our prep for calc, our first unit. So that's y2 minus y1. I'm sorry, y minus y1 equals our slope times x minus x1. Since the derivative is the slope at a point, that's the same as saying the derivative at the point. And we're going to define our point as x as c and f of c. All right, so this is just switching it into function notation. So to recap, f prime of c is our derivative, or instantaneous rate of change at x equals c, and then our specific point x1, y1 in our traditional form, a point slope form, is c f of c. All right, so in this case we're interested when x equals 2, right? So our c is 2. So we need f prime of 2 and f of 2 in order to do this. So f prime of 2, we're going to have 3 times 2 squared plus 3 divided by 2 squared. I'm just using that equation that was given. 2 squared is 4 times 3 is 12 plus 3/4. Right, we want to multiply by 4 over 4 so we can combine our fractions. So I've got 48 plus 3 divided by 4, 51 divided by 4. That's my slope. And then my original equation was x cubed minus 3 over x. So I'm going to have 2 cubed minus 3 halves. 8 minus 3 halves, multiply by 2 over 2. 16 over 2 minus 3 over 2. So we've got 13 over 2. All right, so those are going to be important. We're using our point slope form to find the equation. So our c, remember, is 2. So I just replaced c in our equation with 2. So we got f of x minus 13 over 2 equals 51 over 4 times x minus 2. We could distribute, it's all for f of x, but for now, we're going to call it a die. All right. So next class, we'll get into continuity versus and differentiability, what the relationship is between those two guys, and you'll have some practice to do. For today, just do these notes. Have a great day, folks.